Hi everyone, I am Luca Scimeca and I work in the Bioinspired Robotics Lab at Cambridge University. And today I'm going to be speaking to you about efficient Bayesian exploration for soft morphology-action co-optimization, which is a work we did with Perla Marinino and Fumi Aida for the Robosoft conference 2020. So let's get down to it. So this work is basically motivated by the need of jointly optimize both the morphology and the action of robots. So it is widely known how the morphology has an influence on the way we perceive the world. For example, take the compound eyes of flies, which reduce the resolution of their field of vision in order to allow them to perceive faster action better. Or take our hands. The properties of our dermis, the elasticity of our skin, as well as the shape of our hands or 5 fingers and so on, they shape the way we see the world, they shape the way we perceive tactile sensing, and the way we see objects in our mind. So depending on the kind of task that you want to resolve, surely there is a morphology which can be optimal or very well suited to resolve the task that you want to achieve. It is also true that the action that you, or the trajectory, the behavior that a robot or an animal in the real world for that matter has that can be more or less suited to resolve a task. So this is true for humans. For example, say that you are looking at an object. If the object is stationary and you are stationary as well, you do not move your head, then by looking at the object you can probably retrieve some geometrical properties of that object, perhaps some coloring or texture information. But if you start moving your head right and left ever so slightly, you can start by parallax to realize, for example, that the object is far away or have some sort of understanding of depth information. And this is certainly true for tactile sensing as well. Obviously, depending on the way you, for example, manipulate an object, you will be able to retrieve certain information about that object that you wouldn't have been able to retrieve otherwise. Take, for example, a sliding motion versus a tap or a light touch. They're all different ways of retrieving different tactile information. So if it is true that you can have an optimal morphology for a task to resolve a specific task, then surely you can have an optimal behavior to be able to resolve that task as well. But the optimal behavior that you can use to resolve that same task is dependent in the first place of the actual physical apparatus that you're working with. So the optimal solution for the action surely depends on morphology, but at the same time, if you fixate an action, say you have a walking robot and you only allow the robot to swing its legs of 30 degrees, then surely there must be a morphology which can allow the robot to resolve that task in an optimal way given the action constraint. So morphological computation is something actually that we explored before. So in 2018, our first submission to the Robosoft conference was about morphological computation, and back then we showed that by changing the morphology of some soft filters, basically, you could induce tactile sensing to perform object discrimination by some object properties. So in this case, for example, we're not using any fancy machine learning. No, we're just using simple clustering, so unsupervised learning. But it is possible to cluster objects based on elongation or geometry. So simply by changing this soft filter. So this robot basically just performs a light touch on an object, and it's capable of telling whether the object is rounded or edged, versus elongated or not elongated just by changing its morphological properties, which is basically the thickness of this soft silicon layer, which performs some space filtering on the tactile response and allows the robot to discriminate between a different object based on their properties. So morphology is really important, and morphology can be optimized to resolve a specific task. In the context of sensory motor coordination, instead, this is an example of medical palpation. It's very relevant because medical palpation is one of the examples where action is, through action, it is possible to filter out sensory information, in this case, tactile sensory information, to be able to retrieve complex information from soft bodies. So in this case, the filtering is being done not only by the sensing apparatus, which is a tactile sensor, but also by action. So the trajectory of the hand as it moves over time, which is capable of retrieving more information than if it was stationary, for example. And we did some work which is forthcoming in a robotic journal where a robot will be able to perform this kind of action. So we fixate the sensing apparatus, which is just a tactile sensor, and we change the action to interact differently with these complex, hard, basically nodule inclusions in a soft object. And depending on the kind of action that you perform, you're capable of retrieving more or less information, and thus to resolve the task. So moving on to the optimization of soft morphology action. So in this case, we put ourselves in a scenario where neither the action nor the morphology on their own are capable of solving every single task we tell the robot to do. So we have these 8 objects. These 8 objects vary by different properties. So some of them, for example, are rough. Take object 2, 3, 7, and 6. They have a rough texture, but also they vary in shape. So some of them are squared or edged, while others are rounded. And they also vary in make. So you see here black and white objects. The white objects are stiff or hard, while the black objects are made of rubber, so they present some elasticity. So as you press on them, for example, with your finger, you can feel them bending under your touch. So if the robot is to be able to discriminate between all these different objects, it can do it based on these four different properties. So it can discriminate objects based on roughness, it can discriminate objects based on roundness, or it can discriminate objects based on shape, squared versus rounded. So the robot is given the opportunity to use this tactile sensor, which is the tactile sensor presented beforehand. It's basically a capacitive tactile sensor where every tactile is capable of detecting a pressure. So you have a pressure pattern, and in this case, you have a pressure pattern over time. So every row in this picture is one time slot, and you vary basically through the touch response. You vary the sense pressure over time. So that's why you see these row spatiotemporal data. The kind of action that you apply is basically sliding and pressing motion. So you see this is the end effector, this is the object. The end effector remains at all times normal to the surface of the object, but we allow the robot to basically slide over the X and Y coordinate as well as the Z coordinate, so the robot can move left and right as well as press onto the object. So what happens when you do that is that depending on the action that you use, depending on how this robot is moving left and right and pressing down into the object, the robot will have different tactile responses. But these tactile responses are also dependent on the kind of end effector that the robot is using. So we change the electric layer of this capacitive tactile sensor to have either no roughness whatsoever, or these protruding bits of silicon, basically, of 3 millimeters or 5 millimeters. So the robot is not only able to change its motion, so to change by how much it can slide left and right, or downwards, but it can also change the tool that it's using to sense objects. So it can choose to have a flat dielectric or dielectric with these spikes. So what happens when you do that is that what you can see is you can create density probabilities, probability density functions by coupling every action and morphology together. So you have these 3 different morphologies, and for every pair of morphology and action, you can see how the robot perceives the world in terms of the probability function or the density function, and the distributions, the resulting distributions of using that sliding motion together with the respective tool. Here you see only 2 dimensions because we use PCA to reduce the spatiotemporal data into a lower dimensional space. What you can do also is you can rank the motions based on the distributional overlap. So the more overlapping motions rank lower in general than they would if they were less overlapping. What you can see is also the distributions changing over rank. So this is rank 0 through rank 26. Every one of them is a pair of action together with a morphology, and you can see that the best performing morphologies do indeed separate the data in such a way that it is more easily discriminable. And this can be done over different tasks. So you can see, for example, that for test 2 you will have this ranking, but for another task you will have a different action morphology pair. One other highlight of this is that you can use this idea of ranking to guide your exploration. So as you explore more and more of these morphology action pairs, you can actually avoid grid search methods by instead using this idea of overlap to guide your search. So you're faster if you search in such a way rather than simple grid search methods. So we can see here is the robot actually performing the action, and the change in morphology is actually done manually at the moment. But the robot can perform this lighting action, and what happens at the end of every touch experiment is that, so here it's sensing the tactile response while touching the object, and then every one of these tactile responses are re-encoded into a 2-dimensional space. So what happens is that the robot can just do that iteratively and create distributions for every type of object. Here it's discriminating between rough and smooth objects, for example. So when you do this, you can finally see that the robot is, for example, capable of discriminating between rough and smooth objects by picking a tool or a dielectric which is capable of sensing these roughness, these rough surfaces, and it will pick, together with that rough surface, it will pick an action which makes the robot go back and forth over the direction against the direction of the roughness, so that it can sense it better. For these objects instead, for example, pick something like the smooth dielectric, which better discriminates between them. Thank you.